It's my pleasure, Chang. It's my pleasure to be here, and also thanks to the funding supported by the FBR and the Taiwan, and so that we can bring many of my colleagues to here. And I come from the National Jiao Tong University, and the following talk will be divided into 3 parts. And the first part will briefly introduce the National Jiao Tong University and the work we have done in the past few years. And the second part is about the polariton systems, including the exciton polaritons and also the surface plasma polaritons. And the final part is going to be given by my colleague, Dr. Hong. He is going to present the possible collaborations, the directions in the futures between Taiwan's groups and the Russian groups. So we will involve the hyperbolic materials and also the parity time symmetry breakings, some kinds of the topics of that. Okay, so here's the first part of my colleagues. So he's my PhD student, Shenzhe Huang. So he's doing the photonics on the silicon base. So he's going to realize the systems, optical systems on the silicon insulators. Okay, and the second part is going to presented by my PhD students, Yuxun Zhou. So he is doing the experiments on the polariton systems. Okay, and the third part is going to give Dr. Hong. So he's the only theorist in our groups. So basically, our groups is do the experiments. So he's very good, joined our groups to fulfill the locking parts of our groups. Okay. I'd like to introduce our youngest researchers in our group. Yeah. So he's a PhD student, and he's right now specialized in the nano fabrications. So he can use the focus on beams to create very fancy microcavities using different kinds of the materials. Okay. So we'll start for the first part. Yeah. Thank you.
Okay, I think good afternoon, and this is my name. So I'm the slide of this to give you the presentations of the brief introductions to our schools and our lab, and also I give you the timelines of the history. So the first of all, in this topic, I just mentioned some of the views on our lab. So this is my name, and this is my advisors, Professor Tien Chang. So before we get through our main topic, here I want to show you how far from the Taiwan to here. So the left-hand side, I just mentioned some information about the Taiwan, so you can know about the informations. So you can see this is really far from here to here, and we also take the flight about 10 hours. And the currency, as you can see, $1 NT is about 2 rupees, and it's also you need to be attention is about the AC voltage. So the AC voltage is different from here, so it's about 110 volts. So the frequency is 16 Hz. And also it's the same right-hand traffic.
So large population, really.
Yeah. So it's a high density.
Sorry, and area?
The area is about 36 kilometers square. Yeah.
But we should notice that most of our land is mountains. Yeah, so that makes our density very, very dense. Yeah,
very dense.
Yes. Yeah.
Okay, so next page, I will show you. The next page, the left-hand side you can see is the whole islands of the Taiwan. And I want to show you to focus on the northern part of Taiwan because our school is located on the Hsinchu cities. And this is the Taiwan International Airport. So if you fly to the Taipei, so you will landing in this airport. So you can see the capital city of the Taipei is 15 kilometer distance, and also is far from the 5 kilometers to the Hsinchu city. And so this is the simple image of the different places. So you can see if you have chance to visit Taiwan. And here I also want to show some status of the higher education in Taiwan. So lots of the college is some tops or famous in Taiwan. So you can see the previous is about the public college, and the rest of the college is of the private. So you can see the almost
sorry, this private, the bottom.
The bottom.
the bottom is the private,
Yes.
And
and
Taipei
the-
is capital of your
Capital, yes.
yeah. So most of the college is located on the Taipei, the northern part of Taiwan. Yeah. And our school is also near to the Hsinchu Science Park. So there's a lot of the company, more than 400 companies. So they will have some industries like the semiconductor manufacturing, or some optoelectronic industry, or some information technology industries. Yeah, so it's really closer to our school, just like the Silicon Valley to the Stanford University in the United States. So the next part I will show you our school. We call the National Jiao Tong University. The abbreviations, the letters is called NCTU. That it's located in Hsinchu. So if you are visit to our campus, then you can see the different views of the National Jiao Tong University. So the schedule show the legs, the pro, the swimming and gyms and psychology gyms, and some rooms. So if you are visit here, you can find some pictures in the campus. And here we also have 5 campuses around the Taiwan. So to relate it to the photonics or optoelectronics issues is about the Guangzhou campus or the Tainan campus. So you can see other college for the optoelectronics is called the Qimei Buildings. It's located into the Tainan campus. So if you want to connect to the Tainan campus, you can take the HSR, the train, about 17 minutes to the campus. And then we quickly go through to our department of the photonics. So you can see our institute is founded at the 1980s. So you can see our department is founded also in 2004, and another institute is also founded in 2004. And the faculty, that is the all information for this department. Right now is the latest is about 30 members. Yeah.
What does the Display Institute?
The Display Institute is because we just done some research about the color of the
You need these displays for computers, for
Yeah, there are all kinds of the display
kinds.
technology, including the flat panel display, 3D display, and organic panels. Yeah, yeah, this more engineering oriented department. The institute. Yeah, yes.
So you can see that's a lot of technology to combine to the industries.
And also the technology of color. Yeah.
And you are working in what department?
The departments of photonics includes
Department
two institutes. One is the Institute of Electro-Optical Engineering, and the other institute is called the Display Institute. But the upper part is Department of Photonics. They have 2 institutes.
Yes.
Yes.
And only 27
27 members.
So,
Yeah.
so small?
Yes, it's relatively small. Yeah.
relatively
Yes.
small,
Yeah.
because in our department of physics we have maybe 200
Yeah.
members,
Yes. Yeah.
staffs.
Staffs. Yeah.
Okay, so the next page I will show you about some topic related to our department. So you can see just like some photonic science or information photonics, display science and energy photonics. So also can relate it to the terrestrial photonics, fiber optical communications, or organic electronics, or solid state lightning. So although this kind of goals is our shipment to our department for the research topic. Then we quickly to go through in our group. So our laboratory has three qualities. So you can see the left hand side is the founder of our lab, and the right hand side is now the supervisors of our group is the Professor Lu. And we also show some statistics performance of the Professor Lu. So the journal number is more than the 280. And you can see there are some high impact journals. We are list here. And these are some pictures with the founders of the Professor Wang. And here I just want to show you some history timelines. So you can see the first gas lasers technology lab in Taiwan has demonstrated in the 1965. And the right hand side is recorded the laser stamp in Taiwan, so you can see the picture show about the issues. And then this is the special guest we called Mr. Chang, and you can see the Mr. Chang is visit the laser lab. And the following, the below one I just mentioned, when he was young, he has studied abroad to the laser schools, and because of the policy relation between the China and the Russia, so the Russian people sent him to the Siberia, and then he met his wife. So his wife also became the first lady of the Taiwan. So in 1978, he became the elected president of Taiwan, and that's at the age of 78. And here I just want to show you some research topic about our lab. So the first one is the nitrobase first cells and the pixels. And Mr. Zhou will mention the topic about the polymer lasers and some non-lasers. And in this time, I just briefly give you the introduction to the visual and the pixels.
Sorry, what does it mean, perovskite?
Perovskite.
Perovskite lasers.
Perovskite lasers is our new topics. It's about we use a new type of material. It's the crystal structure is perovskite, but actually it's made of like the organic and inorganic elements together. A typical one is CH3NH3PBI3. Yeah, so it's a very new and very efficient material for solar cell. But we are laser groups, so we're trying to build these kinds of the material into lasers. The benefit of this material is it's a solution processable, so that you can use a very cheap and a very easy technology to fabricate these kinds of lasers. So because it's relatively new, so many people, including our groups, are trying to investigate its characteristics and its potential and what is the advantage and all the disadvantages to realize these kinds of lasers. Yeah.
Thank you.
Okay, so the Mr. Zhou will show you some details in the proton lasers. And for the future prospect, Dr. Hong will give you the ideas and also the plans. So this is a quite important milestones in the 2008. We demonstrate the first low temperature current injection nitron based vessel. So the left-hand side you can see is our the schedule of the devices. So if you are interested in, you can refer to this the APLO journals. And the right-hand side is we demonstrate the world's first room temperature optimum count nitron based pixels. So this is some measurements of our devices, and the below one is the ZnO image of our devices. And here we show you the world's first room temperature current injection nitron based vessels in here. So this is the measurement of this kind of vessel. So more detailed things you can refer to this kind of the APL in the 2010. And also we mentioned in the right hand side you can see we demonstrate the Taiwan first room temperature current injection gallium nitride based polariton LED in the published to the Journal of Nanolater. So this is the more detailed things we mentioned to Mr. Zhou. And here now recently the world's smallest polariton now laser has been demonstrated under the room temperature conditions. So the left hand side shows the image, and the right side shows about the SEN image onto the SES nanos.
Sorry, with silicon oxide, yes?
Yes.
Because your last paper without silicon oxide.
Without, yes, yeah.
And this is so far the world's highest operations temperature surface plasma nanolasers, and also has been demonstrated on the nanolaters. So you can see this is the image, and we try to give the modeling of these devices. And this is also we've done the measurements of this kind of the structures. So here I just want to mention some highlights into the magazine. So there's some topic about the nitride vessel poses the challenge. So the author mentions the vessel structures into this special topic, and other one is about the photonic crystals into the neutrons. So that's also about the gallium nitride pixels and this SPI neutrons. And this is about the brightness enhancement of the indium gallium nitride LED with the VPS issues. So we are the feature articles published on the compound semiconductors in 2015.
Curious, what does it mean? V-shape, probably I understand. What does it mean? Bits.
Oh, it means it's a very special defect appearing in the indium gallium nitride system.
Indium gallium
nitride system. Because we all know that the blue LEDs made by the indium gallium nitride and grow on the sapphire substrates. But the lattice mismatch is huge.
Yes.
Yeah, so the defect density is as high as 10 to the 10 per square centimeters. So how come such a highly defective material can have such a high efficiency? So we attribute to the defects because it looks like the V-shape pits. The pits means the defect. So the dimension of these V pits range from 100 nanometers to 300 nanometers. Yeah, and the quantum well grown on these V pits actually were presented a kind of the high potential well, so that the carriers in the flat quantum wells, they will see these kinds of the barrier heights, and they will not like to jump into the defects within the center of these V pits defects. Yeah, so this we are like the prove and try to demonstrate these effects. Yes.
Okay, so the next page I will show you our group status. So the first one is our members. So we have the postdoc and the Dr. Fong and 6 PhD students, 6 master students, and 3 bachelor students. And also the below one we show some the increment of the applications like the ICV, PCVD, RTA gang. And the measurement of the optimal measurements is about the time result photoluminescence and fluorescence, microfluorescence, and luminescence, and SNO and Tien. And this is the stage of the vacations. So here I just list some facilities about our lab that we use. And this is also mentioned to the Fuchs ion beam systems and also the SEM, the system of the image. Okay, so I think that's the first part of this slide. So the more detailed thing about the research topic were introduced by Mr. Joe. So thanks for your attention.
Thank you. Museum.
Yes. Just like the museum we visited yesterday, Hermitage. It's not a Hermitage museum.
So, okay, good afternoon, ladies and gentlemen. My name is Yuxun Zhou. I'm a PhD student, and my advisor is Professor Chang. Now, I'm going to give you an overview of the polariton-related research topic that our group has done before. So, here's my introduction. We'll discuss about the competition of polariton lasing and p-band lasing in zinc oxide microcavities, and another type of polariton which we call surface plasmon polariton laser in zinc oxide nanowire. Finally, our summary. So let's talk about the microcavity polariton. First, microcavity polariton is a kind of quasi-bosons, which is a mixture of excitons and cavity photons. And the energy will split out to 2 branches, which we call upper polariton branch and lower polariton branch when the system is under strong coupling. So polariton, since it's a bosonic particle, so it has a small effective masses, and it can, in zinc oxide system, it can operate it under room temperature because of the strong excitonic property. So several materials has realized polariton lasing, but however, though the operation temperature requires very low, so it is not practical for us to use in the industry or daily life. So the advantage of the wide band microcavity such as gallium nitride, zinc oxide is it has a larger exciton binding energy, which larger than the room temperature thermal energy, and the large oscillator strength, which will increase the interaction between exciton and the cavity photon. So the next thing I want to introduce is the p-band lasing. So what is p-band lasing? P-band is a phenomenon that exciton scattering. It is a phenomenon due to the scattering between 2 excitons. So one of the exciton will scatter into a lower energy state, and another will scatter up to the electron hole plasma. And so this is an inelastic exciton-exciton scattering phenomenon. So in the next topics, I will talk about the interaction, the competition between p-band lasing and lower polariton lasing in our zinc oxide microcavity.
Would you please tell few words about what do you mean p-band? You mean this internal energy structure of exciton, S state and then one S state, two S state, P state, or not, something different?
Something different.
Something
Yeah,
different.
yeah. It's the inelastic scattering. Yeah, in the dispersion curve show that the two excitons scatter together, and one scattered down to the P state.
P-state.
So that's the
P
P states. Yeah. So it is
in
called
fact, photonic states.
photonic states or the polariton states.
Polariton
Yeah.
states.
Yes.
So I'm here to talk about the polariton lasing in zinc oxide-based microcavity. And this is our microcavity structure. We use an MOCVD to grow up the aluminum nitride DBR, and then use POD to grow up zinc oxide as our cavity layer. Finally, we deposit the silicon oxide half-line oxide DBR as our top DBR. So as you can see, here's our image, SEN image. So this is the experimental measurement.
So what is the quality factor of your microcavity?
It's about 300
300.
at
Because
room
your
temperature.
top distributed back reflector is from isolating materials.
Architecture. Architecture
Yes.
material. Yeah.
Yes. So this is the reflectivity spectra of our structure, and by using the transfer matrix method plus the dipole oscillation model, we can say that our experimental was coincident with our simulation, that our structure is under polariton, is under strong coupling region. So to get a further vision of our devices, we can see that at the room temperature under low pumping condition, most of the polariton will accumulate at the higher K state, which we can call it bottleneck.
Sorry, you have a strong negative detuning between exciton state and cavity.
Yes, this is a strong detuning. Yes, negative detuning. Yes.
Why do you use so strong negative detuning?
This is because if the detuning is very small, the polariton will tend to just escape from the energy trap by the thermal energy. So it will make it harder to condense at the lower state, and thus the threshold will be much more higher in our system. Since we are the
In
laser.
fact, you have a large potential well for low polariton branch, yes?
Yes.
Yes.
But interaction with light is decreased in this case.
Yeah.
And can you estimate interaction strength, for example, like Rabi splitting or something?
Yeah. It can be calculated. Yeah.
Yes.
But, yeah.
It can be calculated in our cases, yes. So once we increase the pumping power, the bottleneck will be suppressed by the polariton because of the polariton interaction will be much stronger. Since we increase the pumping, the system will consist more polariton. Then the interaction between them will be much more stronger. And finally, it will reach the polariton lasing at the proper
10 micro.
10 micron.
yes, at 10 micron.
What are the lasers called?
Pardon?
Laser spot.
Laser spot.
You mean the spot size?
Diameter.
Size.
The spot size is about 10 micrometer.
10 micron.
Yes. So the polariton lacing has a very different characteristic from the photon lacing. As we can see, polariton lacing has a smaller threshold than the photon lacing. And after the threshold, the line width will become broadened due to the polariton-polariton interaction. And furthermore, the energy shift will show a blue shift after the threshold. So this shows that our devices were under the polariton, under the strong coupling conditions. So as I mentioned above, that zinc oxide exciton has a stronger exciton property, which makes it more easier to reach lacing condition at room temperature. So this is our experiment of our zinc oxide cavity at room temperature. So you can see
higher temperature.
Higher temperature, yes, 353 Kelvin. Yes. So it shows the typical polariton behavior, that the line width will increase after the threshold. Yes. So we also have the phase diagram of the polariton laser. So as you can see, this is the phase diagram of the our devices. Okay. So at higher temperature, the escape rate will increases. So if we have a smaller detuning, which has the energy trap was not that strong, so the polariton can escape from the energy trap easier. And for a deeper trap, the polariton cannot escape that easy. So the threshold will be much more smaller. And as you can see, here's two dips in this phase diagram. It is related to the first
So
order.
again, this scale in fact detuning or what? Horizontal scale. During detuning, there is two favorable detuning for lacing, polariton lacing.
Yes. Yes. Yes.
And this is related to the first order LO phonon scattering. And the second dip is related to the second order LO phonon scattering.
Two phonons.
Two phonons.
Yes,
Yeah.
two phonons.
Not second order.
Okay. Two phonons.
Oh, okay.
Yeah.
Two phonons. Sorry about that. So this is the lacing property at 100 Kelvin for small detuning microcavity, which shows no difference to the typical polariton lacing. So interestingly, another emission peak, as you can see here, will occur at a high energy as the detuning becomes more negative, let's say minus 16 millielectron volt. This additional emission is related to the P-band, which is due to the inelastic exciton scattering. So as the cavity detuning becomes more larger, the polariton relaxation efficiency keep decreasing due to the shorter lifetime and less possibility to scatter with other excitation. So the cavity emission will be gradually dominated by the P-band, while the lower polariton branch exciton offset keeps decreasing since the polariton scattering will be decreased with the
Have lacing on that spot,
Yeah.
P-band.
Yes.
P-line.
This is the P-band, and this is the lower polariton branch. So as you can see in the first, in the beginning, the P-band will lacing, and then the lower polariton lace. So here's the light in, light out curve of the P-line lacing characteristic and the polariton lacing characteristic. So here's the simple schematic of our system. First, our laser pump into the zinc oxide microcavity and generate excitons in our reservoir. And the exciton will transfer into two branches. First, the p-band, and second, the upper polariton, and second, the lower polariton branches. So, since the above mentioned, since the exciton number of the system was limited, so the p-band mechanism will compete with the lower polariton branch mechanism. And interestingly, the energy offset of the p-band and lower polariton branch is about terahertz generation. So maybe it can be used into the terahertz applications. So this is, we also done the phase diagram of at 77 Kelvin to 120 Kelvin, which the p-band will highly affect the system. So these two mechanisms, with p-band and lower polariton branch, will started to compete. So which shows a much larger threshold in lower temperatures. So as you can see, this is our phase diagram below 120 Kelvin. Typically, we predict that the threshold here will be lower when temperature lower. However, because of p-band will affect the system, so the threshold at lower temperature will be higher than we thought.
This threshold for p-band only, not for low state. I mean that.
This is the polariton threshold. This is the threshold for polariton lasing.
Polariton lasing from p-band or from the lower state?
From the lower state. And
From
this
the
is the p-band threshold. This is for p-band and this is for polariton. Yes.
But in this case, I still don't understand why at elevated temperature the threshold is lower than at 77 Kelvin.
In our cases, the p-band will appear up to 120 Kelvin. But after that, the p-band effect will be will just suppressed it. So in this temperature ranges in the temperature range from 77 Kelvin to 120 Kelvin, the p-band effect will be much more stronger than the high temperature. So
in fact, at lower temperature, population of p-band may be stronger than lower state. Yes.
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 Yes, that's what. So this is our part on the microcavity polariton. My next topic is the surface plasmon polariton laser using zinc oxide nanowires. So it is a kind of polariton that the surface plasmon generate from the metal surface coupling to the game material excitons. So why we want to have a laser with a nanoscale size? It has a small footprint, and since it is small, so the threshold and the operating current will be much more smaller, and because it made of the metal, is a kind of loosey material, so it can be used in the high-speed modulation. And the above-mentioned advantage will make it possible to using in the bio application, like medical therapy. And the small size make it possible to integrate onto the silicon photonics, especially our latest research on aluminum surface plasmon. It is a CMOS integrable process. And finally, it can use into the optical interconnection. So there are very rare. There are very few articles are talking about the ultraviolet emission in the surface plasma polariton nanolaser. So this is our. This is why we choose zinc oxide as our material, because it emits in the ultraviolet region. And now, here's the schematic of our structure. So first, we use a e-gun to deposit silver onto the silicon substrate. The thickness of the silver is about 200 nanometer. And then we deposit silicon oxide onto the metal surface as a spacer. And we use zinc oxide as our GaN material. So the purpose of the silicon oxide is to prevent the intrinsic ohmic loss from of the silver. And this is our zinc oxide nanowires. As you can see, it's a hexagonal shape. And this is the SEN image. So zinc oxide is a material that emits ultraviolet at room temperature. And the large exciton binding energy will make it much more stronger to couple with the surface plasma. So to ensure that our devices to ensure that the signal emits from our devices is original from the plasma mode. So we have done the calculation by the finite element method. So we adjust the side width of the wire from 20 nanometer to 120 nanometer. As you can see, for the side width of the wire larger than 17 nanometer, there's a waveguide mode inside the wire. And in contrast, when our size of the nanowire is smaller than 17 nanometer, there are only plasmonic mode in the system. So to ensure that our devices will only operate under plasmonic mode, we choose nanowire sizes in between 28 nanometer to 35 nanometer. So it is for guarantee that our devices won't exist waveguide mode. So this is our fabrication step. We deposit silver onto the silicon and deposit the spacer onto the silver. And by doing the DUV process, we can define the pattern on the sample. So why we want to define the pattern is because the way we put our nanowire onto the surface is by by spreading the wire onto the surface randomly. So the purpose of the pattern is to targeting the single nanowire that we can ensure that we pump one nanowire at one time.
What is the size of this rectangular hole on your gold or platinum?
It's about 100 micrometer.
And you believe that only one nanowire will be deposited in this hole?
Okay, first of all, we patterning onto the sample, and then we drop cast our zinc oxide nanowire onto the surface. So because it is a randomized distribution, so it is hard for us to find a single nanowire. But once we found that, we can use those metal hole to locate our position of the wire. Yes.
But
So we
nanowire
cannot
can be
control.
deposited at this gold or platinum surface, not in the
Yes.
Yeah.
Yes.
Hold some kind of mark.
Mark.
It
Yeah.
is a
Both
kind of
Both
mark.
positions. So they use the SEM first to check if the patterns only contain 1 nanowires, and we will record the positions in mark, and then we just measure only 1 nanowires at a time. Yeah.
As you can see here, so this is our SEM image, and besides are some bunch of ZnO nanowire, and we will targeting those wire without any company nearby the wire. In this side, we didn't show, but maybe 1, 2, 3 or something like that. So we can know that there's a single nanowire at number 1 or number 2, and then we can use the OM image to finding the position of the wire, and finally pump onto the wire. So this is the optical characteristic of our silver surface plasmon nanolaser, and this is the photoluminescence spectrum from low pumping to the high pumping. As you can see, at first there are only few peaks, and when we increase the pumping, several peaks will appear. And the mode spacing here is about 1 nanometer, and the corresponding group index calculated by the mode spacing is about around 70. And we also measurement the polarization of our devices, which is parallel to the ZnO nanowire. And by the calculation,
Sorry, once more.
okay,
What are the physical origin of these separate peaks? Are they standing waves or something else?
It's very simple. It's a peripheral modes. Standing wave.
Along this.
Along the, yeah, so it's very surprised that in such a short cavities, only 1 microns, it can sustain so many modes. So that the physics behind that is because the group index is so large. So the calculated group index is as large as like 70 to 80. So that although the length is very small, but if you times this group index, it is kind of like 80 times 1 microns.
Yes.
So that you can sustain so many longitudinal modes in that small cavity. Yes.
And so large index is due to coupling with
The surface
substrate?
plasma.
Surface plasma.
Surface plasma. Yeah.
okay, so this is the calculation from the 3-dimensional model, which consists with our experimental result that are that the signal we observe in our experiment is the fundamental mode here. So the lower group velocity in ZnO nanowire cavity increased the interaction of the surface plasma mode, and the gain median, and moreover, increased the energy density with smaller mode volumes, so leading to sufficient large Purcell factor, which is promising to achieve the ultraviolet surface plasma nanolaser. The effective mode volume for the fundamental surface plasma mode can be calculated to be 4.2 multiple to 10 to the 3 here. So it's the smallest mode volume report for a single emitter in the world now. And to testify that our devices, to testify the robustness of our devices, we increase the ambient temperature of our devices from 77 Kelvin up to 300 Kelvin. As you can see, when the temperature increases, it can survive at 300 Kelvin due to the well confined of these surface plasma mode and the strong exciton property of zinc oxide. And the calculated collection efficiency is about 4.5% here.
You present normalized intensity and real decrease of the intensity from 77 to 300. How large? 10 times, 100 times, or 1,000 times? How large decrease of intensity of output?
Oh,
How much intensity? It's about It's about 1 to 20. It's
times.
Time. Yes.
20
20 times
It's about 20
lower
times.
intensity.
Yes.
And what does it mean, collection efficiency? What do you mean, collection efficiency? And radiation efficiency. This internal output or external output?
External.
External output.
And collection efficiency, what does it mean?
The collection efficiency means that because the typical surface plasma actually binding to the surface, so that it will not radiate. But because we have like the abrupt surface from the nanowire to the surface, so that that discontinuity will create some loss of the surface plasma mode. So that we calculate those like the liquid radiation modes to the volumes. And then because we use the objective lens to collect those lights, so we calculate that the collection efficiency of that objective lens with NA of
The numerical answer is about
0.55. So that's a pure collection efficiency. It's not the actual efficiency. So we use this calculate collection efficiency to like the inverse to estimate what will be the radiation efficiency for this nanometers. Yeah.
Okay, thank you.
So this is the room temperature characteristic of our devices. As you can see, the well-known light-in, light-out curve, S-shaped curve, has observed at 300 Kelvin. And to have a much solid evidence that to claim that our devices is under is under plasmonic mode, is operated under plasmonic mode. So we have done the time-resolved photoluminescence measurement. As you can see, this is our system response. It's about 7 picosecond, and the red line is the signal measured from the zinc oxide nanowire spread onto the silver and silicon oxide surface. So the lifetime is about 13 picosecond, which shows that our devices was under the plasmonic operation.
Is it polyaretonic lasing or usual laser?
Sorry, what did you?
Polyaretonic lasing or not, or usual laser, typical laser with inversion?
The surface plasmon will interact with the zinc oxide exciton. So we think that it's a polaritonic laser.
Polyaretonic laser.
Yes, it's a kind of polariton laser that combine with SPP and the exciton. Yes. So as the mentioned above, that typically the structure we use is the SIM structure, semiconductor, insulator, and metal structure. And the insulator between the metal and the game material is to prevent the metallic loss. However, we found that to operate surface plasmon, it is usually related to the mode confinement factors and the propagation length. And the propagation length and mode confinement factor was highly related to this formula. The epsilon m is the permittivity of the metal, and epsilon d is the permittivity of the dielectric layer. So as you can see, our previous work on the silver-based surface plasmon shows you can see this figure that for silver, the combination of the metal part and dielectric part will be not valid after below the proper wavelengths in here, because of the permittivity of metal is kind of negative, so it will be imaginary, which the surface plasma mode does not exist anymore. So, however, if we choose the right matchup of the metal and dielectric layer, the combination of epsilon m and epsilon d will no longer be imaginary. In our cases, we think that zinc oxide combined with aluminum can so in these cases, we think aluminum plus zinc oxide is more convenient for realizing the surface plasma laser, because it can get rid of the dielectric layer. So we also do the transparency gain calculation in this figure, as you can see. For zinc oxide combined with aluminum oxide. Sorry, I didn't. Sorry, this is zinc oxide placed on silver and insert with aluminum oxide, and this is the zinc oxide placed on the aluminum with aluminum oxide, and this is the width of the aluminum oxide. So as you can see, for zinc oxide placed on the aluminum, if the width of the aluminum oxide nears to 0, it can still have a smaller gain. And in contrastly, for zinc oxide placed onto the silver, the threshold will be increased rapidly at the width lower than at the width nearby 0. So the star represent that the threshold of the devices with no gap between zinc oxide and silver. So, however, above mentioned is the theoretical prediction, but as we know that aluminum always contain a native aluminum oxide after fabrication. So to prove that our prediction is right, so we have to choose high quality aluminum with high dense packing, which will have very fewer native aluminum oxide. As you can see, we use the MBE method to grow the single crystal aluminum, and this is the TEM image after 3 weeks. So we cannot observe so the native oxide was relative small in this case. So TEM cannot. So it is hard to observe in the TEM image, and the AFM of the metal surface is about 0.44 nanometer in 5 times 5 micrometer regions. So this is the optical image of our devices under laser operation. As you can see, the interference pattern that ensure that our devices is under laser operation.
Sorry, about left top image.
Okay.
This the image of aluminum. This
Okay.
aluminum oxidated at ambient conditions, at room temperature and in atmosphere or not?
No, it preserved in the nitrogen.
In
chamber.
nitrogen. But
Yeah.
top part probably is oxygen, aluminum oxide or not?
No, that is
Bottom part, the crystal lattice I see, and top part, what it gives?
the top is just like a artificial.
Ah,
Yeah,
artificial. No oxidation.
Not oxidation. It's the glue to
It's a
prepare
glue to stick on the sample. Yes,
I see.
and has or glue to yes.
You prevent this oxidation, keeping this aluminum in
nitrogen
Yes.
chamber.
Yes. Okay.
Yes, we place
And then you deposit your zinc oxide
Nanowires.
nanowire in this pure aluminum with no oxidation layer.
Yes.
Okay.
So this is the light in light out curve at 77 Kelvin and 300 Kelvin, and because we use a high quality metal film, so and combined with the robustness zinc oxide exciton, so the operation has pushed up to 353 Kelvin, which is the highest operation temperature of surface plasmon polariton nanolaser in the world.
Is it better than for nanowire put on the oxide layer in your previous part of talk?
Yes.
On silver.
Yeah. Previously,
Yeah. In
yes.
previous,
Yes.
in the silver, it's better to insert
So-
that.
In aluminum is better or in silver is better? What case is better? I mean
But the,
lowest threshold.
the lowest ratio actually we can observe in the aluminum base.
Aluminum.
Yeah.
Yes. 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 So this is the comparison of the zinc oxide nanowire directly placed on aluminum, and zinc oxide nanowire placed on aluminum with the gap layers. So this is the statistic diagram of those devices. So we have measured more than 10 devices in each cases. So the average threshold for the zinc oxide directly placed on aluminum is much more smaller than the cases of zinc oxide placed on.
Threshold is lower and distribution is small.
Yes, yes.
Okay.
And for a much more solid evidence, we have done the time resolved PO2 in our cases. So as you can see, for the zinc oxide directly placed on aluminum, the lifetime is the shorter, and then the zinc oxide placed on the aluminum. And here's the room temperature cases. At room temperature, we can still observe the plasmonic operation in our system because the lifetime is much more smaller than the in pure box. If we measure the zinc oxide if we measure the zinc oxide nanowire directly placed on the sapphire, the lifetime is about 300 picosecond. And in this cases, we place the nanowire onto the metal zinc film. The lifetime is about 50 picosecond, so which we can show that our devices is under plasmon operation. So this is my summary. We demonstrate the first observation of the coexistence of P-band and low polariton bridge, and they will compete with each other. And we demonstrate the demonstrate the ultraviolet zinc oxide nanowire base structure. And finally, we realize the high temperature operation up to 353 kg in the aluminum base surface plasmon nanolaser. So thanks for your attention. And the next talk will be given by Dr.
gentlemen. My name is Prof. Hong from the National Jiao Tong University, Taiwan. My talk is about the overview of possible cooperation. The outline includes 3 parts. First is Ling-Arsan nano laser. The second is gallium arsenide big cell. The final part is black polariton, and I will show you the summary about the today's talk. Okay, the first part. In general, the purpose of adding an insulator tip layers is to reduce the large metal loss. My English is limited. Sorry. Okay. In metatonic plasmonic waveguide, so the optical energy can be stored in an ultra small region. In this study, we show the lasing spectrum to demonstrate that our Ling-Arsan nano laser can operate at room temperature. This figure is the SN of nanowire, and the right-hand side figure shows that the OM image, and we can see that the laser light is coherent. So, in this paper, we also numerically calculated the dispersion relation, electric field under different wavelengths, and the transference gain. But we don't discuss the exciton plasma coupling. So we hope Professor adjuncts and members of SO lab can help us solve the debug. Okay.
Mm-hmm.
Okay, the second part is the gallium arsenide big cell. Yeah, we also interested in the gallium arsenide big cell. This figure is the schematic of gallium arsenide big cell with and without circular rings. And the right hand side is the beam view images for those below the threshold and above threshold condition. Okay, in the lasing region, we can see that the beam view image is like a visual game mode. Okay.
Please wait a moment.
Okay.
Consider this. Gallium arsenide vertical gravity emitted lasers. Yes. And this with electric pumping, P dot N dot dBr, yes?
Yes.
And you already realized this laser, yes?
Yes. Yeah.
In your case.
Mm-hmm.
And near field optical microscopy, I
Yeah.
can see so-called.
Okay. In 2014, the famous group of UC Berkeley proposed a PT microring laser. This is their schematic, and the SCM image as shown here. The depth is about 1 micrometer. They fabricate 2 cases. One is typical microring laser and the PET microring laser. In their case, in their structure, they're using the PT breaking mechanism to demonstrate single mode lasing. Yeah, so this topic can solve our problem to reduce the visible gain more.
What do you use? Would you please repeat to reduce what?
Let me explain more detail.
Okay.
So in the previous slide, you can see that previous previously. Yeah, we can see that in the normal case without this ring, okay, we can see very complicated modes patterns, and that it doesn't not only appear in the near field but also in the spectrum. So typically, if you make the VCSELs with a larger diameters, it always exhibit multiple operations. Yeah, but we are thinking that because it is kind of the CRISPR-Gary mode structures, if you can use the PT symmetry breaking mechanisms, like the next slide, like the next
You
slide.
can just deposit some.
We can. We
to
can
select only one mode.
only one mode.
Okay.
That will be very, very helpful and probably very promising to make with a VCSELs with a larger size, operate on the single modes and the high power. Yeah, because typically VCSELs only operates with very small powers, so the applications will be limited. Yeah, so the main application fields for the high power lasers are dominated by the edge-emitting lasers. But I think the VCSELs can have a better geometries in terms of like the heat sink and the fabrication process because it's the vertical. I mean, you can test immediately. So that if we can apply this kind of mechanism, it will solve a very very important problems in
Yes,
mixing the
I
VCSELs.
understand.
Yeah. Yes.
Good.
Yeah.
And the final part is the Professor Alajon's contribution. Okay. They propose a nano quantum mechanism. They propose the GnO blood mirror includes 10 nanometer Indian gallium nitride quantum wells. Okay, so they discuss the linear and nonlinear behavior of this proposed structure. And we can use our famous fabrication to regress these kinds of structure and recalculate the reflectivity or photonic bands. But we don't know the behavior of nonlinear, the existence of nonlinear behavior. Sorry. So Professor Jones can help us to solve this problem. Yeah. So my topic summary is this is 3 interesting topics and includes exciton plasma coupling and the hyperbolic metamaterial or PT symmetry breaking. These 3 interesting topics we can cooperate.
Yes. Yeah.
Yeah.
Okay. Yeah. Yeah. Actually, the first part there's a term called exciton. Yeah. The coupling between exciton and the surface plasma polariton is a exciton. Yeah. So it's another kind of a polariton.
Hyperbolic material, metamaterials.
So I would like to mention that hyperbolic materials is in break polaritons we have a joint paper with Alexei Kavokin.
Yes,
So-
I remember.
So
I
because
remember.
he
Moreover, we discussed with him the experimental realization of this because our growth team can grow
Gallium arsenide system.
gallium arsenide, yes, aluminum gallium system with Bragg reflector and put exciton mode at the top of this stop band. And in this case, just realize this hyperbolic.
Yes.
but I just announced that this is not for me only. There is
Okay.
so we
It's
start
okay.
a collaboration.
Simplify the to let everybody know. Yeah. Okay. Thank you.
Thank you for
Yeah.
your attention.
Thank you.
Yeah. Thank you.
I would like to thank all the speakers. I would like to say that it's really very interesting for us, and cooperation would be interesting also. But we still, how to say, not so close to each other because we mainly is working in blue range. We mainly is working in infrared.
Infrared.
Infrared
Yes.
range.
Yeah.
You mainly working with lasers.
Mhm.
We are mainly working with no laser. Of course, a polytonic laser,
Polyton lasers.
typical polytonic lasers, of course, we are studying. And in particular in ring means some specular picture and so on. But of course, we will show our laboratory, I will continue this understanding, but in any case, I would like to say for our young people, it's very interesting fields for cooperation. So please think carefully about possible problems we can start to study in our lab. So I would like, if somebody
One
have
question.
questions, one question,
I
please.
should like to ask you about the so-called P band in the emission spectrum of zinc oxide. Is it a very specific and peculiar property just of this material? Can you observe the similar light in other wide gap semiconductors?
Oh, yeah. It will usually happens in the wide band materials with strong excitonic behavior. Yeah. So some reports like observe these kinds of like in organic materials. Yeah. But some in the gallium nitride system, but at very low temperature. Yeah. So zinc oxide is a special case. They can sustain at the relatively higher to 100 kelvins.
You need a very strong exciton.
Very strong exciton. Yeah. Yes.
More questions? Okay, thank you again. And now Professor Chang suggests to make
take a picture.
take
Yeah.
picture. So somebody, Dima, could you
Может быть,
please?
зал вначале сфотографировать?
Вот отсюда сейчас сначала сфотографировать.